Okay, today's speaker at the famous experimental mathematics seminar of Rutgers University is Nathan Fox, an alumni from Rutgers, who will speak about game complexity between geography and Santorini.
Thanks, Doron. So at any time, if you have any questions, feel free to interrupt. This is all joint work with Carson Geissler, who was a student at the College of Worcester, which was my previous institution. He studied this game Santorini that I'm about to tell you about for his senior thesis. And most of what I'm going to present here is either previous results or stuff that he did. Though my rule was I won't think about this until your project is over, and then I'll take it and extend it. So some of this has been extensions since then, but and some of this was stuff that Carson did during his project. So first of all, what is Santorini aside from a Greek island that once exploded in a huge volcanic eruption? So it's a board game that this is what the board looks like. So now I'm going to explain what the rules of this game are. So you have a 5x5 grid. It's kind of hard to see because there's stuff on the board, but you have the board is a 5x5 grid. And this position that's being shown here is not the starting position. This is a game in progress. At the start, all the squares look like this, where it's just a green thing with nothing on it. We're going to call squares with nothing on them squares with height 0. And then there are buildings that you can put on the things. So this one has 1 building on it, so it has height 1. This has 2 buildings for actually. Yeah, this one actually I can't quite tell if that's 2 or 3. No, that's definitely 2. There's no building with height 3 in this picture. You can imagine like this building without this cap on it would have height 3. So it would have this little round thing, but it would be flat on top. And then all the ones with the cap on top are of height 4. So you notice there's like these 2 people of the one color and then the 2 people of the other color. These are called workers. Each player gets 2 workers. So here's how the gameplay works. So the first 2 turns, the players take turns placing their workers on any square out on the board that doesn't have another worker. Those are sort of special, and we're not really going to think about those moves too much. Once all the workers are placed, a turn consists of a move and a build. So you move to an adjacent square. And diagonals count. So for example, this worker here can move to that 1 square there. But there are 2 other restrictions on this.
One question.
Oops. Yes.
You move just one of your workers or both of your workers?
You move one of your workers. You can choose which worker, but you only get to move 1 worker per turn.
Can I move through buildings?
As I said, you can move this worker here to this 1, which would be quote unquote moving through buildings.
Okay, got it.
So yes, you can do that. But yes, so you can move diagonally. But what you cannot do is workers aren't very good at climbing. So you can only, if you're moving to a higher level, you can only move up 1 level. You can also stay at the same level or move down any amount. So can't go up more than 1. So like if I had a worker here, I couldn't move there because that's from height 0 to height 2. But this worker can move there because that's from height 1 to height 2. And this worker on here at height 2 can move down there to height 0. That's fine. Workers can move down. They just don't like climbing.
Nathan, what are the blue caps? The dome.
That's the next thing. So the blue caps are height 4. The blue caps, you might notice, are not flat. You can't move onto them. So the other thing you cannot do is you cannot move onto a building of height 4. Those are blocked off forever.
And those caps only go on at height 4. You can't put them.
Yeah, the caps are height 4. Each height has its own shape.
Oh.
Though the shapes are not important, but that yes, each height has its own shape. So,
But do you have a height 3 there?
there's no height 3 in this picture. A height
Okay.
3 would imagine the one with the ones with the cap, but imagine that there were no cap. It would have a
I
little
see.
round
That's
thing on top.
That's the X on the.
Yeah,
Okay.
yeah, it would have a little round thing on top that would be flat on top. None of those are actually in this diagram. So after you move, you build, and building is required. And you also would build on any adjacent square that does not already have height 4. So you increase the height of any adjacent square that's not of height 4.
Adjacent to,
Where you just moved. So you build after you move, and you have to build with the same worker you moved. So increase height of adjacent square.
Is there any notion of these buildings being yours or your opponents? Or
No. The buildings are just part of the board. So when you build, you increase the height of an adjacent square by 1. And there's no height rules in terms of like you could even if you couldn't move high, you could still build up high. So this worker could move there and then build on there. That's allowed. And you can also build diagonally, just like you can move diagonally. And you might be wondering, well, what if I move and then can't build? You can always build where you moved from, because that wasn't a building of height 4. So there's always at least one place you can build.
Can you build on a square in which there's another worker?
Oh, that's a good point. You cannot build where there's another worker. You also can't move where there's another worker. Thank you. So that's how moving and building works, and the players take turns doing that. And then eventually the game ends. So how does the game end? There's 2 ways the game can end. So those of you who have some familiarity with game theory might have already guessed one of the ways the game can end, which is you lose if you can't move. And that would mean both of your workers are trapped somewhere. And that very often does happen. But there is another way the game can end, which is if you ever move on top of a tower of height 3, you just instantly win the game. So we're going to call this the tower win rule. And we're actually mostly going to pretend it doesn't exist for the rest of this talk. Because we're not going to analyze exactly this game. We're going to talk about variance, and the first thing we're going to do to simplify the game is throw out the tower win rule, because it makes analysis much harder. So these are all the rules of Santorini.
So you can build height 4, but moving to
Yeah,
height 4.
but once
is
you
a
build
different-
height 4, you're essentially blocking off that square forever.
Okay.
But another thing, you might want to build to height 4, because otherwise your opponent could move onto that when it had height 3. So that's a way to stop your opponent from winning.
Is it 5 by 5 the board?
It's always, yes, a 5 by 5 grid.
So when you analyze, you do K by K for
I'm
smaller
getting
height?
there. You're getting ahead of me.
Okay, sorry.
Right. So this is an example of what's known as a partisan combinatorial game. Which means that there's 2 players. There's no hidden information, no randomness. And the game will eventually end. This particular game can't end in a draw. Somebody will always win, because there's only a finite number of possible positions, because everything is bounded by the max height, and every move increases the total height by 1. A lot of common games that people play are partisan combinatorial games, such as like chess and tic-tac-toe. And what makes it partisan as opposed to another notion called impartial is that each player has their own workers.
Nathan, will there be gods today?
No, this is there. I know that in the actual game of Santorini, there are gods which change the rules. We're just analyzing talking about things without that. That makes the game even more complicated. Okay, so let's talk about what we can adjust to actually analyze things here. So the two sorts of things we're gonna mess with are what the board looks like and what the rules look like. So the game of Santorini itself is played on a fixed board, and I'm going to be very informal with my talking about complexity today. I'm not going to assume any sort of background in complexity theory. But I will note that you can't analyze complexity without any sort of parameter to parameterize the complexity. So a fixed 5x5 board has no parameters. So you need to be able to generalize the game somehow in order to analyze its complexity. So one obvious generalization would be, well, instead of 5x5, play on an n by n grid. You can go even farther though, and just play on an arbitrary graph. Like a 5x5 grid, that's just a graph with where every vertex is adjacent to all the ones that are adjacent, either vertical, horizontal, or diagonal from it. So why play on a grid graph when you can play on any graph? So our main thing we're going to parameterize is the number of vertices in the graph. So we're going to talk about the complexity relative to how many vertices the graph that we're playing on is.
You're always assuming a square graph?
No. In fact, we're never going to assume a square graph. We're going to always be talking about arbitrary graphs from here on out. And then the graph, the game of Santorini itself is played on an undirected graph, because you can move if you can move one way, you can move the other way, unless there's the rule about heights that's preventing you. But that's a game rule. That's not a property of the board. But you could also play Santorini on directed graphs. So you have to modify the building rule to actually build backwards along the arcs of the graph. So if you're playing on a directed graph, like let's say you have a worker here and there's another vertex here, you would move along the arcs of the graph, but then you would build backwards. That way that preserves the property that you can always build where you moved from. So whenever we talk about playing on a directed graph, we're always going to be assuming that you move along the arcs and you build backwards along the arcs. All right, so then there's all these rules that you can mess with. There's this tower win rule that I've already said we're just going to basically throw out. There's the number of workers, which in Santorini is 2 per player, but we're usually going to talk about 1 per player, or even sometimes 1 shared worker.
One quick question about this last bit.
Yeah.
Yeah, in the undirected case, when you move somewhere, you can build on anybody that's surrounding you that's not of height 4, right? Okay.
Yeah.
In the
Yes.
directed case, you
can
move
still
somewhere, and then you can move to any. Build on any vertex that is back. Oh, I see.
Yes, so you could build on any of those, but not this one.
Right.
Or sorry, yes, that one, not that one.
Yes. Okay.
So you can't build here. Of course, you could have arcs going both directions between 2 vertices. That's allowed. But there is a rule that we're going to mess with, though, which sometimes we're going to restrict building to be only where you moved from. So we're going to say that you can't actually build anywhere else. So the only build that's allowed is the one that you always have. That's a rule you can tweak. Yeah, and then you could also tweak this upward movement restriction. And you could also, as I said, add shared workers to the game, where it's a worker that either player can move. And then if the game would end from that worker, you just treat it. It depends on who moved it.
And the nodes have heights, do they?
Not in the nodes will still have heights, yes. Not in this schematic picture here, but this is just demonstrating one thing at a time. But yeah, just a note about this shared workers thing. Whenever we have 1 shared worker, we're going to call that the impartial game. And 1 worker per player, we're going to call that the partisan game. Plus a bunch of other rules that will vary from version to version. Okay, so let's talk a little bit about game complexity. As I said, I'm going to be very informal because I don't want to assume various background on complexity theory. But for those of you who do have this background, I do want to tell you precisely what I mean. So when I say a game is easy in this talk, I formally mean that finding a winning strategy is in P. So computationally, it's easy to describe a winning strategy to the game. And if I say a game is hard, I'm specifically saying I formally mean P space hard, because that's a common class for talking about game complexity. But what you should just think is it's like chess, where obviously someone has a winning strat. There's obviously a way to play chess optimally, just because there's no randomness and there's perfect information. But there's no chance that we're ever going to figure out how to play chess optimally. It just would take way too much computational power.
So here, do you mean finding a winning strategy given like a certain initial condition of the
given,
game? Or...
Yeah, I mean, given a certain initial condition, not just given like an all empty initial condition.
Okay.
So that way you can describe it all recursively. So this is what I mean by easy and hard. So easy, you should sort of have tic-tac-toe in your mind. That's not a perfect example because that's one fixed game, but sort of something where it's more like a puzzle than a game. So easy games are puzzles. They're not really fun games to play. They're parlor tricks. Whereas hard games are actual fun games because even though there's theoretically a best way to play, it's fun to explore the game. So how do we actually say how hard a game is? And really the way we do that is we actually compare games to other games. So we say game A is at least as hard as game B, again, being very informal here, that you can simulate game B using the rules of game A. I don't have an easy example of this, but we'll have a bunch of concrete examples in the rest of the talk. So like I don't have like a schematic example here, but we'll see a bunch of these. And these are known as reductions. These are a common tool in complexity theory. And for those of you who know some stuff about complexity theory, I am hiding some details here. Yeah, and sometimes it's the case that you can use A to simulate B and you can use B to simulate A. And in that case, we say the games are equivalent. So if you're always just comparing games to other games, how can you ever say anything? We need a starting point. And thankfully that we have a starting point. This is a classical game that is known to be quote unquote hard. And it has various names, but I'm going to refer to it as the TQBF game. So the setup is something we call a 3CNF, for 3 conjunctive normal form Boolean formula with, we're going to say 2n variables, x1, x2, up to x2n. So what this looks like is you have clauses that have 3 of these either variables or their negations, which we usually write with a bar over the variable. So this is a Boolean formula. So these things are either true or false or 0 or 1, depending on your favorite way of thinking about this. Every clause is an or of 3 of these things. And then it's the whole phi is an and of all these ors. And it could have as many clauses as you want. And we say 2n because we're always going to assume there's an even number of variables. So the rules of this game, so suppose Abigail and Brian are playing the TQBF game. On the first turn, Abigail chooses a truth value for x1. So Abigail decides x1 is going to be true. Then it's Brian's turn. Brian decides, aha, I'm going to make x2 be true. But you always have to go in the order of the indices. The last move of the game, Brian decides whether x2n is going to be true or false. And then after all the moves have been done, you plug in the truth values that Abigail and Brian chose, and you check if the formula itself is true or false. If the formula is true, Abigail wins, and if it's false, Brian wins. So this is equivalent to a non-game version of just checking if this expression is true, this quantified Boolean expression. So this game is equivalent to this decision problem. And this game is classically known to be p-space hard. So this is a good starting point for a lot of other games. Okay, so here are some basic reductions we can do with Santorini. So Santorini on general graphs is going to be at least as hard as Santorini on grids, because that doesn't actually change the rules at all. Any grid is also a general graph. So if you have a way to find a winning strategy for general graphs, it will also find a winning strategy on grids. You just apply it to grids. Normally directed graphs are at least as hard as undirected graphs, because a directed graph or an undirected graph, you could just replace an edge with arcs going both directions. If you add additional workers, you're not making the game any easier, because you could put those workers on isolated vertices, or you could surround them with towers of height 4. And then you're essentially just playing with one worker, because the other workers are just trapped. And also, if you increase the max height, you're not making the game any easier, because the starting position with max height 4 on that 5x5 grid is, if the max height's 7 instead, you could imagine starting with all the squares have height 3. And then it's the exact same game. Here's one that's a little bit less obvious. That playing with max height 2 is actually at least as hard as with max height 1 if there's no tower wins. So let's talk about why this happens. So obviously this means that max heights 1 and 2 are actually equivalent, because this means that max height, because this last thing we talked about means that max height 1 is at least as hard as max height 2. Actually, I think I have this one stated backwards. I mean the non-obvious thing. I meant to say that max height 1 is at least as hard as max height 2. The surprising direction. And the way we do that is, so here's a game with max height 2. So let's say we have a height 0, we have a height 1, we have a height 0, we have a height 1. Here's what we can translate it to with max height 1. You split every vertex that's a 0 into 2 vertices, and then connect them to all the corresponding things. If you have 2 zeros next to each other, you would connect in a K2-2 like that. And the reason this sort of thing doesn't work if you go beyond max height 2 is then you start running into the you can't move up more than 1 level rule. But that doesn't ever come up if the max height is 2, because you're never going to be able to move on to a tower of height 2 in that situation. Okay. So now I want to state the assumptions we're going to use going forward, and then the rest of the talk will be analyzing specific variants. So we're going to be assuming general graphs, directed or undirected. So we're not going to be playing on grids. We're always going to be assuming there's no tower wins. We're always going to be assuming there's either one shared worker or one worker per player. And we're also going to always be assuming the max height is 1 unless we state otherwise explicitly. So as that previous thing said, if any result we get for max height 1 also applies to max height 2. We have the same upward movement restrictions as Santorini, so you can only move up at most 1, or you can move the same level or down as much as you want. And we're also going to sometimes have this restricted builds rule, which is where you only build we're only allowed to build on specifically the place where you just moved from. That rule is going to be there sometimes, but when I say the term restricted builds, that's what I mean. So here's the first variant I want to look at. Impartial. So there's one shared worker on directed graphs with restricted builds. So let's say the worker starts there. So essentially what you're doing, so all these things have height 0, and then when you move, the place you moved from has height 1. So you move this worker here, this has height 1. So you're essentially just deleting it from the graph after you move from it. So this game of move a worker, take turns moving a token around on a graph and delete the vertex you moved from, this is a classical game known as geography. It's based off of a children's game where you name cities and you always try to you always have to start the next city's name with the last letter of the last city that was named, and you can't repeat cities. So this is a generalized graph theory version of this. And this game is classically known to be hard. And here's a picture of a reduction to show that you can actually simulate the TQBF game under the rules of geography. So at the start, it's Abigail's turn, and Abigail, if she wants to make X1 be true, moves to the left. If she wants X1 to be false, she moves to the right. Then Brian's move is forced. He has to move he has to always move to here. Then Abigail's forced to move there. Then Brian gets to set a variable, and then they take turns. So eventually Brian will set this variable. Abigail will be forced to move there. Then Brian gets to choose a clause by moving to the corresponding clause vertex. Brian, if the formula is false because it's a conjunctive normal form, Brian will be able to move to a false clause. If Abigail has succeeded in making all the clauses true, has succeeded in making the formula true, all the clauses will be true. Then Abigail gets to move to a variable within the clause. Since each clause consists of all ors, a clause is only false if all of the things in it are false. So Abigail won't be, so if the clause is false, Abigail is moving to something here that's false. But if the clause is true, she can always move to something that's true. If she moves to something true, Brian loses because this will have been deleted when this variable was set. But if Abigail moved to something false, this is still here, Brian moves there, then Abigail loses because this vertex has definitely been deleted. So this classical reduction is due to Lichtenstein and Sipser. And it'll actually be the basis for a bunch of our other reductions. We may not have time to see too many of them, but this is an important thing to keep in mind. This is a good structure for these reductions. Okay, so we're going to sort of thinking of geography as sort of our base thing. So I kind of think since we can obtain geography as a variant of Santorini, that really means that we should probably think of Santorini as a variant of geography, because geography is more of the classical game that people study. So let's start with this as our base. So whenever I change a rule from geography, I'm going to italicize it up in the title of the slide. So now we're playing undirected geography. Same rules as geography, but every edge is undirected. So that can't change much, right? So the only thing we're changing is that if you have an arc going this way, you also have an arc going that way. Otherwise, the rules are the same. There's no way that changes the complexity of the game, right? Actually, yeah, it does. So undirected geography is easy. Due to Frankel, Scheinerman, and Ullman. The way to win is, so this red dot down here, if you can't see the red dot, I just circled the vertex for you. If the vertex with the worker is involved in every maximum size matching of this graph, Abigail chooses one of the matchings and wins by always moving along edges of that matching. So the purple edges here in this graph, so this edge, this one, and this one, those are a maximum size matching because it's a perfect matching. So if you have a perfect matching, that's a maximum size matching. So there's other perfect matchings in this graph, but you only pick, Abigail just picks one. So Abigail will win by moving here. Then no matter what Brian does, Abigail can move along the next one of these and so on. And eventually Abigail will win this game.
In this game, there's just one worker.
Yeah, when I say impartial, there's just one shared worker.
Okay.
And Nathan, on this theorem, is this due to two different people who are parents of people associated to Rutgers?
At least one, and possibly two.
Okay.
Oh, Scheinerman,
The Scheinerman?
Scheinerman, I know.
And if that's Jeff Ullman, that's Peter Ullman's dad.
That's
Uh,
unlikely.
No, this is
Uh,
actually Peter
I know
Ullman.
this Ullman. I don't think it's the same.
No, this is Dan Ullman.
Okay,
Dan Ullman. Like I know his name because he's now the Putnam director.
gotcha.
Yeah.
Okay.
And then Frankel is Frankel.
No,
He's given a
Frankel,
talk at the
Frankel.
seminar before.
Obviously.
So what if we change the rules to undirected geography to allow unrestricted builds? That actually doesn't change anything. So Abigail can win with exactly the same strategy. And a way to see this is, suppose she couldn't win with the same strategy. So sort of think of this picture now. So if Abigail could not use the same strategy, so let's say she tries it, that's her matching edge. She moves to that vertex. This one's gone. The only way Brian could really theoretically win here that he couldn't win otherwise would be to move somewhere and then delete a vertex that is along a matched edge. Because otherwise Brian is essentially just playing the other game and he knows he'll lose that game. But now the graph that's left, well, the worker's here now. These two vertices have been deleted. So Abigail can just pretend that this edge was in the matching and these two weren't. And so this blue edge here plus all whatever other purple edges are in the graph elsewhere, that's a maximum size matching of the graph that's left. So in other words, Abigail can just move right back here and put Brian in the same bind he was in before. So the same strategy works. Okay. So we're back to restricted builds now, but I've added another rule. So this was all with max height 1. So now we're playing undirected geography, but max height is 4. So that means you're not deleting vertices, you're building on them, and they effectively get deleted once they've been built on 4 times. And there's that moving restriction. So this feels like maybe it's a small change. But this actually is enough to make the game hard. And that's because we can simulate geography in this game. So the previous reduction we saw was from this TQBF game. But you can also take other games, such as geography, and use them in reductions. So you'll notice that every vertex in this graph for this geography game has been replaced by 5 vertices in a path. And the heights on these vertices are 2, 0, 1, 3, 3 in order. So I'm going to refer to this as a meta vertex. And the directionality, so all the outgoing arcs from a vertex, they all come out of this last 3. All the incoming arcs, they always go into the 2. So they're undirected in this graph. All the edges in this graph are undirected. But you can translate from this back to this by using that property. If whatever is incident to the 2 is an incoming arc, and whatever is incident to the 3 is an outgoing arc. And this initial worker is on this 2 in this corresponding vertex in the meta vertex. So let's talk about why this works. So I'm going to call this game, where the game that's played on each meta vertex, I'm going to call this game very cleverly 20133. The board for a game of 20133 is a path with 5 vertices. And the initial heights in order are 20133. The max height is 4, and the worker starts in the 2. So what properties does this game have that we care about? Well, one property is this is a bipartite graph, which means that you can tell whose turn it is just by looking at where the worker is. You don't care about what the heights are. So if the worker's on this 2, on this 1, if the worker's on either end or in the middle, it's going to be Abigail's turn. And if the worker is in either of these vertices, it's Brian's turn. And that follows from the fact that this is a bipartite graph. And that's very important for making the analysis of what we're about to do tractable, as otherwise there would be just an explosion of cases to consider. Playing the game of 2-0-1-3-3, Abigail playing first would lose this game. But suppose that if she's going to lose, she prefers to lose by being trapped on the rightmost vertex. She can always make sure that happens. So what I've drawn down here is what we call the game tree for this game. Well, I've pruned a few things off of it. But the way this game plays out is the first 1, 2, 3, 4 moves of the game are all forced. There are no choices to be made. But then Abigail has a choice. So in this position, the heights are 3, 2, 2, 3, 3, and the worker is in the middle. Abigail can move either left or right, and neither one is any worse than the other for her. If she moves to the right, down to here, Brian will move to the right, because otherwise Brian will lose according to that orange path. On the other hand, if Abigail moves left over to here, Brian has 2 choices, and he could make either choice, and neither would be worse than the other for him. And moving to this, well, now all the heights are 3, so you're forced to end up there after 4 more moves. And down here, you end up forced to go here, unless Abigail wants to lose without getting to the right, which she doesn't. So one of these 3 green positions will always be reached. And in the context of gluing a bunch of meta vertices together, like we did up here, since the rightmost vertex is the one that connects to the next meta vertex, this means that play will always progress from one meta vertex to another. And so if Abigail's starting on this meta vertex, she's eventually going to choose what meta vertex to go to next. And importantly, once a meta vertex has been departed from, effectively the vertex that was derived from in geography has been deleted. Because suppose that you're traveling around in this graph and eventually you're going to re-enter the remnants of this meta vertex. Well, the remnants either start with a 4, start with 3, 3, 4, or start with 3, 2, 3, 4, because those are these 3 green things here. And we can ignore anything after a 4 because a 4 is in the way. You can't move on to a 4. So obviously this is just blocked. This 3 right next to it is because that's the 3 from the previous meta vertex. So if it's Brian's turn on the previous meta vertex, if this is just a 4, Abigail just wins immediately. If it's 3, 3, 4, Abigail will win. And if it's 3, 2, 3, 4, Abigail will still win. So in effect, this means that playing through a meta vertex deletes the corresponding vertex in geography. And then the last thing we need to worry about is what I call backing up. We have to make sure that you can't break sequence and move backwards through the meta vertices, which is a problem when you have this undirected thing. And this is solved because the first player would win if you start on the 3 on the right instead of the 2 on the left. And this win does not involve the leftmost vertex. So if Abigail, if Brian ever decided, oh, I'm gonna cheat, I'm gonna move from, if Brian ever says, oh, I'm here, I'm gonna move there, Abigail can immediately win that game. And Abigail would just move here, and then the rest of the moves are forced, and Brian will be trapped between these 2 2s here. So if you try to violate geography's moving direction, you will be punished. So the way I found this game 2-0-1-3-3 is I just used a computer search to find the games with these properties that I needed. So this is the experimental part of the talk. So it's I need a game that has basically all these properties, or I could tweak them a little bit. And this was the simplest thing I found that I could splice in there. But I did the same search for some other variants, like max height 3. Because I mean, max height 1 is easy, which means max height 2 is going to be easy.
Nathan, so this is the minimal. So 20132
It's
not work.
oh 20132 doesn't work. I think this is minimal just by exhaustion. Like I don't have a nice proof that it's minimal, but I didn't find anything smaller, and it's not too hard to search everything smaller. Though I wouldn't be surprised if you splice in smaller things and it's still hard to, it's still p-space hard on the resulting game, but that would require some other reduction. So I tried this for max height 3, so only 0s, 1s, and 2s. And I tried it for unrestricted building. But the problem with both of these is it's really hard to either punish backups successfully or to prevent chained backups. The chaining of the backups is prevented by this thing happening. Because if you could get all the way back through a meta vertex, then you could go back through another meta vertex. And then again, you have a combinatorial explosion of cases to consider. Okay. So we have looks like about 6 minutes left. So I'm just going to quickly blitz through a few other games that we studied. And then I'll just end with some open problems. I'm not going to go through any details of these other things because we don't have time. I just want to show some pictures. So impartial directed with unrestricted builds. So this is geography, but you could delete any vertex you could have moved from. This is a hard game. This is a reduction that Carson found. And you need to double all these vertices. So because like you could move here and then delete one of these, you always need to make sure there's still a path back to these diamonds. And then there's a bunch of buffer nodes or various other things. Like now the variables are going to their opposite in the diamonds, and that's because of a bunch of parity considerations. But otherwise, this reduction is very similar to the geography reduction. Partisan geography, which is directed, restricted builds, but each player has their own token. This game, Frankel and Simonson proved that this game is p-space hard, and in fact, they proved that it's p-space hard even when restricted to bipartite graphs with degree at most 3. This is not their reduction. This is Carson's reduction. That's a slightly different reduction. It has the same starting pieces, but it sticks them together in a different way. And this reduction is what he used to then turn into the next one, which is the same game with unrestricted builds, which I'm not going to try to explain what's going on here. I didn't try to draw it myself because there's a lot of buffer nodes and parity checking things in here. But a reduction that looks like this, it's kind of a variant of this, proves that partisan geography, where you can build anywhere you could have moved from, is p-space hard. And then there's a couple cases with partisan and undirected geography, because we've seen that undirected geography impartial is easy unless you make the build height 4 or higher, then it's hard. There's some open things in between. There's, of course, the restricted builds variant, and there's the unrestricted builds variant. So the restricted builds variant, known as undirected partisan geography, in that same 1993 paper, Frankel, Scheinerman, and Ullman, they didn't actually prove that this game is NP hard, but they said it follows as an easy reduction from Hamiltonian path. And if you know anything about reductions and about Hamiltonian path, you can kind of see this, where you just have one player has their vertex on has their worker somewhere in a graph that may or may not have a Hamiltonian path. The other player has their worker on a path of the same length. So if the one player can move through the Hamiltonian path, they'll win. Otherwise, the other player will win. But that's not a p-space problem. That's an NP problem. But this is a preliminary result that I've proved that this game is p-space hard. I'm not ready to present that yet because that's a very complicated reduction that I need to very carefully check. And then the unrestricted builds version that I also think I have is even more complicated. Like I have pictures of them, but there are so many pieces that I have to be very sure that I'm right before I say anything other than preliminary result attached to these. All right, so to end, there's a lot of open problems. And of course, you can add whatever open problem you might be thinking of that's not on this list to this list, because you can really vary any rules you want or any other things you want here. And I sort of listed these in order of my interest or order of how I feel are important. And the thing I'm most interested in resolving is, what is the truth for impartial, undirected, restricted builds with max height 3? Because that's that case where we know it's easy for 2 and hard for 4. My gut tells me it's probably hard because these games tend to be hard unless there's some clear reason why they're not. And then there's the similar question for if we unrestrict builds for any height, at least 3, where again, my gut tells me that these are going to be hard, but I don't have a reduction. Then there's the question of what if we only play on grids? None of these reductions that I've presented can be embedded in grids. So that's a real question of whether playing on grids is still p-space hard. Again, my intuition that games tend to be p-space hard unless there's some reason for them not to be tells me that yes, this will be still be p-space hard on grids, but I don't have a proof. Then there's the question of tower wins. Carson proved a couple fairly trivial results about tower wins, such as tower wins with max height 1 are dumb. But there's a couple other silly things you can prove with tower wins. But aside from that, we don't really know anything about general interesting games with tower wins. And then I mentioned those worker placement moves at the start of the game. What if you throw those into the game? Can that, like geography where you get to pick where you start, is that still hard? I think that's actually known to be hard, but some of these other variants, we don't know. Similarly, the games that are easy, like what if you play undirected geography where both players are 2 workers? Is it still hard? Or where there's 2 shared workers? Is that still easy? Then there's the question of restricting the starting position, which somebody asked a question about. Parametric dependence on max height is an interesting one, where I've always been treating the max height as a fixed constant and parameterizing just on the size of the board. And that's because as you increase the max height, the length of the game increases exponentially. So it's not clear that these games are in p-space anymore. So these games, when they're in p-space, are actually p-space complete. But if you make the max height a parameter, that's no longer necessarily the case. And in fact, I would be surprised if it were the case. But that's not something that you've studied. And then you can vary the various movement or building restrictions however you want. Or again, as I said, there's lots of other directions you could go with this. But hopefully this was just a nice introduction to this, the world of geography variants as you take geography and try to make it look something like this game of Santorini. And it looks like it's 5:48. So I'll stop here. Thank you.
Thank you. Any questions? First, I have a quick question. Going back to the original Santorini 5x5 case, is there something that a computer can easily beat you?
No.
Oh, it's still.
I mean, no, as in no one's written it. I would not be surprised if the answer is yes, just because of the power that computers exist. Like if someone wanted to do that, they could. Like Carson didn't just study complexity. That's just the direction I was interested in continuing. He also did some AI stuff with Santorini, and he made a program that could sometimes beat him, which was his goal. But this is not a very well-studied game, so no one has really tried to write a strong AI for it. But I imagine that typical chess engine stuff would probably make better than human Santorini players much more easily than it makes better than human chess players. And we have better than human chess players. So I'm sure AI.
But it's hard. Isn't it like the space?
Yeah, well, I mean, Santorini's in p-space. Even if you make the grid n by n, Santorini's in p-space, chess is not.
5x5 is already non-trivial.
Right, 5x5, we don't have a brute force solution to 5x5.
So 4x4, well, what's it? 3x3 probably is okay.
3x3, I bet you could brute force. 4x4, maybe.
So
I mean, there's a lot of possibilities. If you factor in move build pairs, like if you're in the middle of the board, there's like 128 branching factor in this game tree sometimes. So there's a bit of a combinatorial explosion here.
Okay.
But when you analyze this game, unlike chess, it's not obvious how you would create a static move evaluation. So in chess, the way you avoid having to look forever is that you the rules of thumb about piece values and such that give you an approximate value of a position. How would you even, do you have any idea how to do that for this game?
Well, Carson came up with a few heuristics. One was it's usually better to be near the center of the board. It's usually better to be close to your opponent's workers without having them be close to yours, which is possible if you think carefully about how you can configure pairs of workers. Like you could have one worker keeping both of theirs in check. And then he did like one other thing, like you want to tend to be higher up, which these are just sort of human heuristics. And these tended to play better than not having them. I think neural network approaches are probably the way that would end up being best here, where you just sort of train an AI to play against itself and learn from its mistakes. But that wouldn't really give you any intuition. It would just give you an unbeatable computer.
Nathan, have you tried playing against the bots on board space? I mean, I'm pretty sure.
I have not.
They're
I've actually
terrible.
only ever played this game once, and it was against Carson. So I'm mostly
Okay,
interested
it's
in
not
the
a bot.
complexity theory of these geography variants.
Did you win or lose?
I lost, which is to be expected because he has played this game much more than once, and I have played it once.
Now in this is sort of unrelated, but in Hey, That's My Fish, one moves a penguin off of an ice floe and then removes that ice floe from the board. Are you aware of any work relating that to geography?
I'm not aware of any work on that game, which I wouldn't be surprised if it does exist. And it sounds like it's related to geography, but I'm not aware of any work that's been done.
Yeah.
More questions?
David, did you just say, "Hey, that's my fish"? Is that the name of that game?
That is the name of a game in which one has penguins moving on ice floes. Yes.
I look forward to board games coming back sometime in the grad lounge then.
That'll be great. When that happens, I'll come back and visit again.
I used to be decent at Hey, That's My Fish, but that's no longer the case.
And Nathan, the 3 CNF game, is it the actual game that people play for fun?
No, I mean, I don't know anyone who's ever played that game, except like in a computer science class, like in a computational complexity class, I've played that game. But that game is mostly there as just sort of a basis for proving that games are piece-based hard or piece-based complete. And that's just because the alternating quantifiers, which that's like your classical piece-based complete decision problem, the alternating quantifiers lend themselves to thinking in terms of taking turns and sort of game trees, because like Abigail with her existence has to play her existences based on what all the possible things Brian might choose are, and things so on and so on.
Any other questions? Well, let's thank Nathan again. Thank you. Great talk. Thank you.
Thank you for having me.
Thank you.
All right, thanks everyone for coming out. We will see you back here again next week at the same time for our next speaker.
Thank you.
Bye, everyone.